Okay, continue on with the Metos series of videos. We're going to look at disease models in potatoes. So again, the biological factors for the disease, key is the environmental conditions in the crop in terms of potatoes, which we'll see. You got to have the host, the pathogen, and all these factors need to be present for that disease to actually cause an outbreak. If it's a newly emerged disease in the area, the inoculum levels may be too low for the pathogen to cause an outbreak. So the disease triangle explains this well. We have the host, which is the potato crop, the environment, which can tip the scales in favor of the pathogen to overwhelm the crop's natural defenses. So we need to know in-field very specific weather conditions now for the development of this disease. We need to know what the temperatures are, humidity, leaf wetness periods, and rainfall events, which then drives the disease process. The disease process itself has its own management issues, things like call piles or infected seed, which cause the original spore release in the early spring to summer. And then that infects the tissue, which then can cause secondary infections throughout the year. So this is a multiple spray disease, which is governed off the environmental conditions, which can either shorten the spray window or lengthen it. So the importance of localized weather data cannot be underestimated in this case. We cannot drive a model for potato late blight off of data that's 10 kilometers away. We need to know the conditions in the field. And that's what this shows you is we have one at a main office under a grass and one in the actual canopy. We see very clearly here a very large significant period of disease development, high humidity and leaf wetness periods. The one under the grass environment, shorter period, much shorter period for disease development, lower humidity, and lack of leaf wetness periods. So we need to have that station at the field so that we get the proper data to drive the model. And it shows the model sensitivity to the differences in location as well. So in the potato production system for FieldClimate, there's a whole host of models available to you for a variety of things, from aphid, Colorado potato beetles, a lot on late blight, and other diseases as well. Today we're talking about two very common models, better known as a Tomcast model and a hybrid of that called the no blight model. So the value proposition for diseases in potatoes and the late blight models is very high because of the impact of this disease over the entire year and then the effect it can have on storage as well, secondary infections. So with a very site-specific weather station, you know the modeled conditions for your disease risk. You can time your fungicide applications based on the actual conditions and the risk pressure from the model. So you stretch or shorten your spray window, which we'll see, and you'll actually preserve the yields as well as the quality of the crop on a well-timed fungicide application. So the Tomcast late blight model, one of the first that developed, it's a computer-based model to predict fungal disease development. It's driven off of data over a 24-hour period, and it may result in the formation of what's referred to as a disease severity value, or a DSV. So if the conditions are conducive, the DSV values will climb during a day. So you can see an increment of from nothing to as much as 4 in a day. So the DSV accumulates, the disease pressure continues to build on the crop, and when the number of accumulated DSV values exceeds a spray interval, an application of fungicide is recommended to relieve the disease pressure. And this, of course, then is whether it's a contact or systemic. Will change the period of efficacy as well. These disease severity values are shown in a graph, as well as the sum for the period of time. And the first interval, depending upon location, can vary between 15 to 20 DSV points. And when they exceed that, that's when the first spray is recommended in an area. After that, then you look at the 7-day change in the DSV value is important. So, for example, if you have a 0 to 3 in 7 days, that's a low risk. 4 to 8 is a moderate, and a 9 or above is a high risk. And again, that could be a high risk, but you have a product at control of X period of time based on the type of product you're applying. So the Tomcast model shows up like this within FieldClimate. We have it highlighted here. We can see the weather conditions, the humidity and temperatures. You can see the leaf wetness periods, and you can see the DSV values for each given period when they accumulated. So we can see here that there was a 1 or there was a 2 on this day, and then it goes along. So what we need to do is come up with the total number over a period of time, and when that goes past 17 the first time, that's when the first application will be applied. The total in this period from June through August is 52 in terms of the DSV values accumulated. Of course, these DSV values are a matrix between the periods of leaf wetness, humidity, and temperature for any given period of time. So the no blight model, like the blight cast, weighs relative humidity more importantly than the rainfall events. So the spray interval becomes shorter with the accumulation of an inch of rain over the previous 7 days under the same number of accumulated severity values. No blight differs from blight cast in that the accumulation of values is based on relative humidity. No blight does not stop accumulating conducive conditions when the humidity drops below 90%. That's a critical factor, so above 90%. So in an 18-hour period, the relative humidity greater than 90% will accumulate severity values dependent upon the temperature, average temperature. So 3 values at 18.3, 2 at 13.3, and 1 at 10, and 0 at 4, or above 29. So once the severity, in this case, reaches 18 after accumulation of a period of time, that's when the first fungicide application is recommended. The value of the predictive model is to provide the users a reliable estimate of when the conditions are conducive and not conducive for the development of late blight. So the model provides some guidance on when a grower can stretch the spray interval and with minimal risk, as well as when the spray interval needs to be reduced or tightened up with the crop is at risk, because the crop is at risk. So we'll see that here. In this case, we're looking again at the no blight. Here we see the DSV values climbing. So we have a 4, it's more sensitive to the humidity and leaf wetness. And you can see the spray intervals here. So these are the disease severity values. On the other side is the spray interval. So as the disease severity values climb, the spray interval gets down to 5 days in this case. As it dries out, it goes up to 14 days, and it stays long during this period of time because there is no real disease severity values. And again, as the values climb, it shrinks the spray window. So it's providing some guidance on the spray window, and of course that's dependent upon your type of product, contact systemic, and the control period of that product. So the impact of potato late blight is quite substantial in potatoes, especially on the yield and more so on quality. So we have the ability with field-specific solutions for proper disease modeling and assessing the changing of risk levels. There's a number of different models. The number of spray applications is dependent upon, of course, the level of inoculum, variety, susceptibility, type of product, and the environmental condition. And the spray interval can vary substantially based on the local field weather data, hence the need for local weather stations in a potato crop, anywhere from 5 to 12 to 15 days dependent upon the conditions that occur. So the worst conditions, of course, are under those moderate temperatures with high levels of humidity and leaf wetness. So the ability is in software to look at the length of that spray interval. You can stretch it or shorten it dependent upon the field specific conditions, which of course protects the plant and reduces, it can also reduce the amount of product and application cost if you're stretching the window. So reducing one spray on a 300 acre crop, if it's $19 per application product, that's $5,700 of savings on a $300 acre crop. So if I spent $1,500 on my investment, it's still a 4-to-1 return on my investment. If you look at it another way, if it's robbing the crop in terms of yield and quality, you may have a larger field, and I'm going to lose 10% yields on my field on $300 per acre. Well, then we're talking about over an 800 acre crop of potatoes, $240,000 lost income. In this case, I may have multiple devices in multiple fields. So my cost of my IoT device is $10,000, but my ROI in this case is still, very good at 10 to 1. So, whether it's a small individual field or a large field or fields, there's still a very good return. And then, we're not looking at the secondary effect that this has in storage as well in terms of quality. So you really know before you go, you save time and money. It verifies the field weather conditions. You have a verified model of infection conditions, the verified severity of the infection, You have a timing of when to spray, hour and date. You also have an indication of the spray length in terms of short or long period. You have a record of the past infections and when the events occurred as well. And there's also a spray cast model inside that allows you to time your sprayings in addition to the environmental conditions. Thank you.